Hello, calculus scholars. Today we're going to do skill 23, which is implicit differentiation. So you may be asking, what does implicit mean in the context of calculus? And you'll kind of see why I put implicit in here in parentheses, because we're going to kind of take a look here at a implicit versus a explicit type of function situation. So a lot of the times, like when you were in, like an algebra 2 class, you had a y equals, so this is what we refer to as explicit form. But sometimes you'll see, particularly things like equations of circles, for instance, Pythagorean theorem, even some of our trig, our area formulas are actually written in implicit form. So they don't have that kind of y equals type of thing where, there's that clear separation of independent and dependent variables. So what we're going to kind of be working towards is being able to do like rates of change problems, even with like area formulas, volume formulas, and we need to know how to do the implicit process, which we're about to kind of organically build up to. And I really like the way that Delta Math helps us organically get there. So you may want to, take some time right now and copy this discussion of implicit and explicit on your notes. So I would pause the video and do this. All right, so your first exercise today is just derivative notation level 1. So what this is saying, and what makes implicit hard for some people, is what these symbols kind of mean. So this just means take the derivative with respect to w. So in this case, we know that w is kind of like our dependent type of variable here. So I have 5w to the 4th. And remember that the derivative of sine is cosine. So this is just like taking the derivative with respect to x, except the only difference here is that we have w's instead. And on this one, I have n's. So on this one, this is with respect to n. I just write this as 3n squared. And remember, when you're taking the derivative of cosine, this is where you're going to be seeing that sign change. So this is derivative notation level 1. The next thing that we're going to kind of build to is derivative notation level 2. So what we can kind of see here is what is kind of going on is it's asking us to take the derivative of 2w to the 4th plus 3 sine of u in terms of only u. So here are some things that we have. We have that w equals to 4u cubed minus 4. And then we know that dw du, so the derivative of w with respect to u, is 12u squared. And that 4 goes away. So if we're kind of looking at this as sort of the general problem here, here's what we can kind of say in regards to this. So in this first part over here, I'm going to write this as 8w, but we are not quite done with this term. We have an equation that 4w, and this is why it's called implicit. So we have the 8w, and then anytime that we are taking the derivative with respect to u, well, guess what? W depends on u. And this is why we have to write dw du. Now, on the second term here, this is a little bit more straightforward. So this would be 3 cosine of u. Now, guess what? I have an equation for w in dw du. So I'm going to do that. So my equation for w is going to be 4u cubed minus 4. And then my equation for dw du is going to be 12u squared. And our goal is that we only want this in terms of u. So you may want to take a pause here and ask ourselves, okay, how did I get from this step to this step? So I would say that if you kind of take a moment and think about that, you will kind of get this implicit idea very, very well. All right, so now it's just a matter of cleaning things up. So I got 8 times 12. So this is 90, let's see. Yeah, 8 times 12 is 96 u squared. And they do like you to kind of clean it up just a little bit. And this is your final answer. Now, if you felt a little confused about this example, we're going to do another one. And I want you to kind of take note of the pattern here. But it will be a very similar one to this. All right. Now, this one is just in terms of like x's and y's. Our goal is to get just in terms of only x. So what I would do here is I have the equation for y, and then I have dy dx I can do, and that's just going to be 4x. Now, if I want to find d dx, so the derivative with respect to x, no, here I got a y term. So I'm going to just take the derivative of this. So I have 15y squared. Now notice, I took the derivative of y. And y depends on x. So this is why I have to put a dy dx. And then on this one here, I got the derivative of sine of x. So I take its derivative and it's cosine of x. Now I don't have to write dx dx because guess what? This is already in terms of x. All right. So now I have an equation with y and x, but it needs to be only in terms of x. So now I'm going to substitute y and dy dx into the expression. All right, so on this one then, I would put the expression for y. So I have 2x squared minus 1 squared. And then the dy dx is just 4x. and then we can just leave the cosine of x piece alone. And 15 times 4 is 60x. And then we're done. All right, so these are just expressions. Now we're ready to go to implicit equations, and that's where we're going to be doing the full implicit differentiation process. So let's take a look. All right, so what I like to do on this one, I'm going to take the derivative. All right, so the derivative of 2 is 0. The derivative of y squared is 2y. And because y depends on x, I'm going to write this as dy dx. And then the derivative of 3y is 3, but y depends on x. So I'm going to write dy dx. And then on this side of the equal sign, I have a minus 2x plus a 6x squared. So note, put a dy dx after you take derivatives with respect to y. What you may see, like on the delta math, you may see when you are looking at the solutions that they write it as y prime. That does mean the same thing. Okay, so now what we want to do is we are going to look at what these terms have in common. So on this side, I have a dy dx on two terms. So I'm going to write dy dx. And there's not really much that I can do to the right side. So what I did here is I pulled out a dy dx. And then now I need to get dy dx by itself. Now this is dy dx times 2y plus 3. So if I divide by 2y plus 3, these cancel out, and I am left with dy dx equals to negative 2x plus 6x squared over 2y plus 3. And notice here that this is the expression for the derivative of y with respect to x. And notice that it is in terms of both y and x, but it is an equation nonetheless, and we were able to do that. So just to recap here, you put a dy dx anytime that you're taking a derivative with respect to y, because y depends on x. Then, after that, get the dy dx's together on one side. On this one, it already is together on one side. You pull out a dy dx. And then the magic happens, where we get dy dx by itself by dividing, what we kind of, pulled out. And then we have the expression for dy dx. Let's do one more at level 1 and see how this works. All right, this one is still level 1. Now on this one, let's see. So this is telling us to take the derivative with respect to x. So on this side, this is a pretty straightforward and basic derivative. And then on this side, I'm going to write this as negative 2y dy dx. And then I have a minus 3y squared dy dx. And then now I'm going to pull out a dy dx. We get a negative 2y minus 3y squared. And then get dy dx by itself. Cancel. And then you're just left with dy dx equals to negative 8x over negative 2y minus 3y squared. And this is completely your final answer. All right, now let's go to level 2. Now, on this one, it's level 2 because we do kind of have an element of a product rule on this one. My advice is to kind of just do this. So my x, let's see, so I got f is x. My f prime is going to be 1. My g is y, and my g prime is going to be dy dx. So if we kind of write our product rule, we get x dy dx plus y. So we just kind of like worked that term. Now, if you're really savvy, you could kind of do this product rule, not separate, but I like separating it the first time. All right, so if I'm taking the derivative here, this is 0. Derivative of constant is 0. And then this term is going to be your x dy dx plus y. And then my derivative of negative 4x is just minus 4. And then on this side, my derivative of 5y is 5. It's going to be a 5 dy dx. Note, we want to get dy dx on one side. So what I would do here, I would just move this 5 dy dx over to the other side. And hold on a second, just cross this out here. I think I just wrote one too many here. So what I meant to say was I have x dy dx minus 5 dy dx plus y minus 4. And then I'm just going to kind of move those non-dy dx terms. So I got x dy dx minus 5 dy dx equals to negative y plus 4. And then we're just going to pull out the dy dx. This is just going to be x minus 5 equals to negative y plus 4. So our dy dx is equal to negative y plus 4 over x minus 5. And that is completely done. So thank you very much for tuning in. I really encourage you to kind of take a look at these examples that we just did and kind of know, when do we write dy dx. So anytime we're taking a derivative, with respect to y, that y does depend on x. So that's why we have to write that dy dx. And we always want to get that dy dx on one side, pull it out, and then get it all by itself. So thank you very much for tuning in.